Welcome everyone to this episode of Manufacturing Talk Radio. I'm Tim Grady. I'm here with Lou Weiss, who's the founder of Manufacturing Talk Radio. He's also the president of All Metals and Forge Group, our sponsor. If you're looking for open die forgings or seamless rolled rings, particularly for making large gears like the ones behind us, check it out at steelforge.com. Joining us today is Greg Hayes, who is the Senior Vice President of Applied Technology at EOS North America. We're going to be talking about 3D printing. Greg, welcome to Manufacturing Talk Radio.
Thank you so much. I'm excited to be here and see how this conversation goes. I think there's a lot to talk about. I'm not sure if we have enough time, to be honest with you.
I can tell you now we don't. But
okay.
Let's move forward. So tell us about EOS. We'll start with that.
Perfect. Yes. So EOS is an international company. There's about 1,500 employees spread throughout the globe. And we are very proud to be the world leaders in powder bed additive manufacturing technologies. So what that means is we make machines, the software that controls those machines, and the materials that go in those machines to 3D print or additively manufacture components out of both metal and polymer materials. So if you look at 3D printing in the world, there are many different technologies out there. Some use a liquid resin technology, some use an extrusion or a deposition of powder. We use a technique which is called powder bed. So there is a thin layer of powder which is then melted together with a laser system.
I'm fascinated, Greg, to know how the laser knows how deep to go. Does it build a part up and materials added, or how does that actually work?
Yeah, it's really interesting. So EOS celebrated this year, I think, our 32nd birthday. So we are quite old when it comes to the world of additive manufacturing, and we've been developing the algorithms to control these lasers around powder beds since the company's beginnings. And it's really quite remarkable. It's a complicated process, and it takes a lot of fine tuning of the system to know exactly what's happening within the melt of the material as the laser moves around the surface. So if you look at the metal process in particular, this is effectively analogous to a laser welding process. So you're laser welding powder together, and then you're laser welding on top of a laser weld, on top of a laser weld, on top of a laser weld, building it up. And it's not the case that once the material is laser welded that's finalized, because when you put a new layer on there, actually the current layer that you're melting, of course, melts a little bit into the layer underneath of that and the layer underneath of that. And so there's a time temperature history for the metallurgists out there, which is very crucial to the success or failure of an additively manufactured metal component. But we've been developing those algorithms for the past few decades, and have gotten very good at it. And it's really that's our core IP that differentiates us from some of the others doing similar things.
So I have a question about that, technical, I guess metallurgical at the same time.
Yeah.
What kind of structure, molecular structure, is the end product of a 3D printed product?
Mm-hmm. Yeah, it's a really good question, and I think it may be frustrating to hear the response, which is it depends, right? But it depends. It depends in a lot of really good ways and a lot of interesting ways. So just as a for instance, if you fine tune the process, you can create molecular structures or grain sizes within a metal, which are very analogous to say a forged component or somewhere in between a casted component and a forged component. So you'll have grain sizes on a typical magnitude across the material. You'll have mechanical properties which are similar in the X, Y, and Z directions. You'll have fatigue properties, which are also to be expected for the material that you are making, and you'll have densities that are greater than 99.8%, very dense components. You can do this in such a way because of how you optimize and fine-tune the process. But if you want to do that, there's always trade-offs in a process. And so another way to exploit the technology, which some companies have been doing, is they've been either running the process faster or doing it in such a way to save them time and money and sacrificing some properties of the material. So if you are only making a material which needs to have, for example, casted properties, and you're okay with a little bit more porosity, and you're okay with a slight degradation in your mechanical properties, you can save time and thus save money, run the process faster, and then you'll have morphologies within the metal which are slightly different, more analogous to a casting. You'll have porosities which are more analogous to a casting, and the mechanical properties that go along with that. So it really depends on what you're trying to get out of your final component.
Well, if I have a part that I need to make,
Mm-hmm.
let's say it's an aerospace part, and typically you have the AMS specifications.
Yeah.
Is 3D printing yet under the guise or the umbrella of the AMS specifications? Or is there not specifications yet developed for 3D printing?
Yeah, that's a tricky one. They are in development right now. I think you may know better than me when the AMS updated specs are going to come out, but right now there is no final spec, I don't believe, that's been published for additive manufacturing. But there are a lot of organizations, not only AMS but also ASTM, which are working on standards and working on protocols for these types of parts. And in different industries, companies have been able to qualify components to be used not only in the aerospace industry, but also via the FDA in the medical industry for implants, for structural components in airplanes, and for components in other industries as well. So it's being used today, and specifications are being developed kind of in parallel.
As I recall, the International Space Station has a 3D printer up there so that they can repair parts, make new parts, instead of sending another spaceship up for $1 billion. So they must have some level of requirements, mechanical, physical properties already in place, at least in that out of the world environment.
Yeah, I think if I recall the article I read, I think last year sometime, they needed a wrench or some kind of simple hand tool, and someone had built that wrench, designed that wrench here on Earth, sent the file up to the International Space Station. They were able to build that component there, which is an awesome demonstration of what we're always talking about when we talk about distributed manufacturing, right? Because we can design, test, and then lock down a build file, send that build file to another piece of equipment somewhere in the world. And as long as the raw material is there, I think in the case of the wrench, it was an extrusion process. So as long as the filament was there, they're able to then produce it, which is unbelievable. And
amazing.
something out of the movies from 50 years ago, which is what's happening today.
Right, right.
I love that particular reference because when I watched Star Trek as a young kid,
Yeah.
I looked at it purely as science fiction. Our children and your children look at it and go, "Oh, that's cool. I bet I could make that."
Yeah.
And they do.
Exactly. You know, I was having this conversation in the last weeks. I went and visited an eyeglass company when I was in Germany, and they were 3D printing the frames of eyeglasses, and they could use just the phone or the camera on your phone to scan your head, 3D prints the frames of the eyeglasses, put in your prescription that the doctor says you need, and you have a pair of glasses. And the interesting thing for me was they were advertising this and marketing it not as 3D printed, but as customized. And this is a really fundamental shift that I think is awesome when you look at the technology around additive manufacturing. Is that it's becoming more and more that tool in the toolbox that everyone has and everyone is able to use, and we don't need to talk about it or give it a special name. It just is there. It's something that the modern engineer and the modern manufacturing person has access to and understands how to use. So it's when the CNC machines came onto the market, they were new, and now it's commonplace that they're in every manufacturing environment, and additive is coming that way as well.
I'll bet those eyeglass frames still cost $700, no matter what you do.
But I think they were about half of that, but it's still a lot of money. That's
You bet. You bet. That's one of the highest profit margin consumer items that there is.
Yeah. It's really interesting. It's something that also can be manufactured in a distributed environment, right? You don't have to make all the iframes in one location, depending on where you're shipping them around the world as well. I think it's really interesting.
Oh, it's fascinating. Craig, you have been in this a while. What are the most unusual things that you're running across? Because manufacturers all over the world are looking at this technology saying, ooh, I could build that. What are the unusual applications?
Ooh, I mean, one thing that the common person may not know is that a majority of hip, knee, and spinal implants are 3D printed today by a variety of medical customers spread throughout the world. And I think this is really interesting because when you need a knee replacement surgery or a spinal implant surgery, you oftentimes don't discuss the manufacturing method with your doctor, right? You discuss what the medical remedy is going to be. So I think that there's a lot of marketing and understanding that can be done today on just applications that exist. But the medical industry for me is really interesting, followed probably closely by the modern space industry. So by space, I mean basically rocketry, propulsion, and communication technologies. So there are a lot of companies today which are looking at solving problems like, how do we get a number of small communication satellites up into space in the fastest and cheapest way? How do we look at things like human space travel, which is less expensive than what it's ever been before? And the propulsion engines that have historically been used can be redesigned, lightweighted, and improved in their thrust to weight ratio to be able to enable this new industry. And so there are a ton of companies using additive EOS technology, but also many other additive company technologies to enable this kind of modern day space race. And I think that's super cool and a great example of what can be done.
So let me ask you a question about down the road, decade, 2 decades down the road. Is it ever going to get to the point where 3D printing is going to be making nuts and bolts and so on? You can go to the hardware store and pick up a tool and everything's going to be 3D printed.
Let me counter your question. Is it the case that you need to forge and then machine every nut and bolt that's made today?
No.
Okay. So similarly, also no, right? I think.
Okay.
I don't think that 3D printing is a replacement technology at all. I truly believe that it is an additional tool in the toolbox that manufacturers will have access to, that engineers will have access to. And so, you know, your high volume, mass produced components, which are typically made now, the nuts and bolts of the world, I don't see a lot of that changing. But what I do see changing is next generation engineers who will be proficient in computer-aided design systems, who will have knowledge of how to design components for additive manufacturing. They may be sitting behind the computer and they may say, you know, this assembly, which previously was 10 or 12 components and consisted of therefore, 8 different weld seams and 4 bolted connections, no longer needs to be designed in these different components, but we can design it as one component and print the entire thing itself. So maybe in the future, then we're going to need less nuts and bolts than we do today. But printing those nuts and bolts, it's a big ask that will become financially advantageous using an additive technology.
Greg, I'm curious about EOS. They're the manufacturer of the printer, the
Correct.
3D printer.
Yeah, that's right.
What are the parameters now and the size of the part that I can print?
Yeah, so we have like all new and emerging space technologies, we're constantly making improvements. Right now, EOS offers basically 3 different sizes of machines. So we have small, medium, and large. The largest machines at this moment can print something which is 450 by 450 millimeters by 1,000 millimeters high. So it's if you think of a box of that size, 450 by 450 by 1,000. If it fits within that space, you can potentially print it. However, we are making progress every day in demonstrating larger build envelope sizes, and not only larger sizes, but also technologies to speed up the process while controlling the process in better ways. So we are doing all types of equipping the machine with in situ sensors, so we know exactly what's happening at every single voxel of space inside of that build, and we can guarantee that it's a good part and a successful build that comes out of it. All the way to thinking of ways to double the size of the large printer that we have today. So these technologies are ever expanding.
So those who are still trying to calculate 400 by 400 by 1,000, that's 16-inch by 16-inch by 40-inch, which is a rather sizable part. And certainly if it's made out of steel, you're talking about really a weighty part. But I wanted to point out, and I think you and I spoke about this, about the bridge in, I don't know if it was Sweden or Norway. They built a 3D printed bridge that went across a narrow stream, maybe 20, 25 feet. I'd be curious to see the size of the machine, the printer that printed that, or were they all printed in bits and pieces?
Yeah, I think that's a really interesting point that you bring up. I think because I think it highlights the fact that when we say 3D printing, we mean a variety of different things. So EOS, the company where I'm working and representing today, we concentrate on powder bed fusion technology. So this is in a controlled environment where we're using a laser to melt a powder together. It offers really high resolution. It offers great mechanical properties, but it has these size limitations that we just talked about. As we sit here right now, I'm actually talking to you from a small city in the south of the Netherlands, about an hour away from Amsterdam. And in Amsterdam, on the canals, is the 3D printed bridge, which you are talking about, which is not 450 millimeters big, of course. It's, I don't know, 20 feet or 50 feet long. And this bridge was not built using EOS technology, but it was built using another technology, which has a deposition head on the end of a robotic arm. And so they're able to feed material into this robotic arm, deposit it as they go, almost like a sophisticated metal hot glue gun, and move it around and build up the material as you go. And they're able to therefore construct this bridge almost freeform out of nothing. And it dawns on me that I've compared their technology to a metal hot glue gun, and that's not fair at all, because it's much more sophisticated, and I don't want to cause any adverse reactions. But I just trying to simplify the description of it. But it's really cool, and it's a great demonstration of what's possible. I think it's awesome.
Have you visited it?
I have, yeah. I definitely have. I've walked across it, yeah.
That's very cool.
The question is, did you visit it and walk across it?
Of course, yeah. Of course. You cannot. It would not be right of me to go all the way there and not, of course, walk across.
Of course,
Yeah.
of course.
Greg, sometimes demands are for thin wall or a very fine thickness. What's the capability of the EOS printers there in terms of how thin the part can be? Yeah,
so that's interesting. So that's an area where, of course, it's constantly being improved upon as well. We use a powder material feedstock. So the thickness and the fine detail features that you're trying to create with a laser and a powder, of course, are dependent on the size of the laser beam, and they're dependent on the size of the powder as well. Right now, I think we reach a lower limit of somewhere around 75 or 100 microns in some of our really fine detail resolution recipes that we have. And that's about as thin as you can go with a process which is what I would call production ready. Of course, in a laboratory setting, in an experimental setting, you can push the limits further. But that's with an EOS technology. Some other technologies, for example, polymer printers, which utilize a liquid resin and not a powder, they're able to go even finer in resolution detail. But they have other trade-offs, like the mechanical properties aren't as good. The parts have a lifetime effect because there's some degradation in the materials and thus. So it all depends on the application. You have to balance and weigh the pros and cons.
So, Greg, what does the Senior Vice President of Applied Technology actually do or be involved with EOS?
Yeah, that's good. I have an awesome job, which I would not trade for anything. I run the technical teams in North America for EOS. And what that means is we have a number of engineers which work on all different types of projects. Some work on internal development projects, like how do we incorporate a new type of laser into our system, or how do we work together with our German engineering teams on a next generation system, all the way to customer related projects. So a customer is asking for a new alloy, which has never been printed before. Can my team figure out how to print it, and what the properties of this material are, and what the recipe to print it is, all the way to application projects for our customers. So we do a lot with either existing customers or potential customers that come to us and say, hey, we have this component, we want to print it, we're not really sure how. We have to think about qualification, we have to think about cost per parts, we have to think about some sort of like distributed supply chain to make this part in the future. Can you help us? And in a consultative way, we engage with those companies, and we help them get from an idea on paper really into full-blown production. And we do that 50, 75, sometimes more than 100 times a year with different organizations, and that's really cool. And the other part about my job, which is really interesting, is in doing all of this and working with customers, we recognized that there was a huge gap in the skill level and the knowledge needed by companies to put this technology into real practice, and the education, skill level, and knowledge readiness of the employees that they had. And so a number of years ago, we started an educational and training branch of EOS, which I also oversee in North America, called the Additive Minds Academy. And it's all focused on workforce development, training, and education across additive in many different topics. And this spurred out of a need that we had as we were trying to grow the industry, and we saw this was a pain point. We tried our best to try to address it and fix it. And I think what we're trying to do now is get what we've learned and what we've built as this Additive Minds Academy into the hands of those 4-year schools, of those 2-year schools, especially to really train the workforce of the future.
Considering that the workforce of the future is going to be smaller and smaller over the next 20 years.
Dude, I'm not sure I totally agree with that. I think some of the advantages of things like additive manufacturing, but also things like reshoring and the CHIPS Act that was just put out there, are really bringing manufacturing back to Western countries, which have been focused on globalization for such a long time. We see a lot of reshoring happening. So I would agree with you that that the hardcore manufacturing jobs as they exist today may become less, right. But the total number of jobs, I think, is going to actually increase in the manufacturing sector. They'll just look slightly different than what they have in the past. And there was, I was listening to a Navy general talk a number of weeks ago, and he was talking about manufacturing and how it relates to the Navy. And he made a point that really resonated with me. And he's like, we're not talking about white collar jobs or blue collar jobs, but right now with these type of technologies and the workforce development programs that we have, we're talking about new collar jobs. So he's created a new type of collar, so not white collar, not blue collar, but new collar jobs. And I think it's maybe a slogan, but I think it resonates a lot with what we're seeing in the manufacturing industry today.
It'll probably be more like a white jacket job.
Could be a white jacket job. It will involve a computer in one way or another. I'm certain of that.
Right.
No doubt. Greg, just to wrap this up, one of the things we want to be sure that our viewers know is how to get a hold of EOS or reach out to you so they can ask their questions and present their projects.
Perfect. Yeah. So if I plug the website, so you can go to either eos.info, that's our global website. You can also go to eos-na.com. That's our North American website. All of it is connected and easily searchable. The workforce development programs and consultative services that we run are under an EOS brand called Additive Minds, which you can also Google and easily get in touch with us. I'm not sure, Tim and Lou, if you post my email address, but if you want to put that at the bottom of this recorded session, more than happy to send me a notes or find me on LinkedIn, and I'll make sure that they get connected in the right way to our organization.
That'd be terrific. We're pleased that you are here.
Yeah.
If you have any new stuff coming down the line, perhaps a 32 by 32 by 80-inch long melted steel out of titanium, so you can save on weight. Let us know, and next time we'll even put up a couple of photos of what your machines look like.
Yeah.
That was my fault. I should have suggested this to you in preparation, so I apologize for that. But it looks like you have a wine still behind you. So I don't know if that's part of your printed material or is that part of your habit.
No, my wife's family helps run a restaurant brewery here in the Netherlands, where I am currently, like I said. And so I'm sitting in the museum, which is attached to that restaurant brewery right now, coming to you live from the Netherlands. But when it comes to additive manufacturing, I believe strongly in this kind of crawl, walk, run methodology. And so I would encourage everyone to reach out to us, see what they can learn. On our websites, you can be connected to our online store, and you can do all types of e-learning courses, some of which are even for free, just to get your hands a little bit dirty with the technology and see what's possible. I think it's really cool, and we're there to help, and excited to do so.
Great stuff.
Perfect.
Yeah, great stuff. Greg, thank you again for being with us.
No problem. Happy to do so, and hope to see you guys soon. Thanks again. And
while you folks are surfing the web, stop by eos-na.com or eos.info to check out all the cool technology that is here today. If anybody thinks that manufacturing is dull or boring or dirty, wrong. It's all really cool stuff, and Greg is on the cutting edge of it, and so is EOS. We appreciate having him with us. Also, check us out at jacketmediaco.com, where you can find over 1,000 podcasts that we have produced, and we look forward to you visiting us in the near future. Thanks for being with us on Manufacturing Talk Radio.